Hey everybody, welcome back to another video lecture for Chem 107, and we're in Unit 4, and in this lecture we're going to be talking about Chapter 26, and by 26 I mean Chapter 25, and in Chapter 25 we're dealing with trends on the periodic table. Now before we get started too much in this, I do want to try to come out with the definition of this word trend. Okay? And that word trend means a pattern. I think it's no joke that as we've gone through the past few chapters, that there's patterns that arise in the periodic table. The most important of which may be the electron configuration of elements. And because we know the electron configuration of the elements, we can then predict the charges, which we had just talked about in the previous lecture in Chapter 24. But because the electrons are similar across the periodic table by similar rows, meaning all of these guys have the same number of valence electrons, and then all these guys have the same number of valence electrons, and all these guys have the same number of valence electrons, and because properties are determined primarily by the electrons, this sets up that we can find patterns, different types of patterns in the periodic table other than just charge on the ion. And the three that are the most important are size, meaning usually the radius of an atom. Remember, an atom is usually a sphere, and then the radius is the size from the nucleus in the middle to the outermost electron here. Okay, so it's a radius usually it's measured in. And then ionization energy, that's everybody's kind of favorite one, or at least chemists' favorite one, because ionization energy is the energy it takes to remove one electron. And so if we have a nucleus and we have electrons, we can figure out how much energy it takes to remove one electron from here, okay, from the valence. And that's there. It's not the energy to remove 2 electrons or to remove 3 electrons, but it's the energy it takes to remove 1 electron. And then electronegativity is a great periodic trend because this pattern is really dependent on the shape of the periodic table, or is not dependent on, but is easily determined by the shape of the periodic table. And it also talks about how electrons are shared, but not in an atom, but when we have a bond going on, when we're dealing with a compound. Okay, so the thing to keep in mind about trends and patterns, however complex this seems, it's not really that difficult. But the thing to keep in mind is that we're going to use fluorine, which is this element right here, and we're going to use francium, which is this element right here, to be kind of our pinpoints for which way and how things move on the periodic table. Okay, and so how trends are kind of patterned. So we'll talk about francium. We'll say, hey, it gets bigger as it approaches francium, or smaller, or it goes this way. And so we're always looking at francium and fluorine to be the kind of the pin of the trend. So let's first start talking about atomic size, because this is the most important of all the periodic trends. So atomic size is really dependent on 2 things. And this one right here, the number of shells, that's the most important thing. Okay? So the first one, when we do this, let's say, nucleus, if we have an electron here, or an element with an electron here, like hydrogen, versus an element like lithium, where its outermost electron is in the second shell, that makes it bigger. Okay? So that's why the Bohr model of the atom is really good at teaching this. Okay, Okay, we'll do the extreme. And again, this should be a circular orbit. I just don't add it all the time. So if we have an electron here, let me go back here. If we have an electron here, that's one size. But then if we have an electron out here, this one is much bigger. So as we go down the periodic table to francium, the atoms get bigger. Okay. And then, and this is what happens, as we move across the periodic table, the atoms get smaller. So fluorine, well, actually it's helium, but we're going to keep using fluorine as our example. Fluorine is the smallest element. Okay, helium is, but helium doesn't do anything. It's a noble gas, so it doesn't do anything. So on our periodic table of elements that react, we're going to say that fluorine is the smallest. Okay, and then this is the smallest, so then it gets bigger as we move towards francium. Okay, and so now when we go to ionization energy, this is based on the size of the atom. Okay, and so if we have a nucleus and we have an electron here, this electron is highly attracted to the nucleus here, and that means that it's really hard to remove. And so that means that it has a high ionization energy. So smaller atoms have high ionization energy. And then the opposite is true. If we have an electron way out here, this electron isn't attracted as much to the nucleus, and it becomes easier to remove, and it has a low ionization energy. So the bigger the atom, the smaller the ionization energy. So that means that francium is the smallest ionization energy. And fluorine, again, because it's the one that we use, fluorine has the biggest. So that means that ionization energy increases moving like this across the periodic table. Okay? And electronegativity is very similar to ionization energy, except in this case we're not dealing with atoms, we're dealing with atoms that are bonded in a compound. So that makes it a little more complex. But the point is that because it's related to ionization energy, this fluorine, because it's the smallest atom, means it has the highest. And this is how we abbreviate electronegativity, because we don't want to write out that 15-letter word. I think it's 15 letters. We abbreviate it ENEG. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Electron is 8, and then negativity 9, 10, 11, 12, 13, 14, 15, 17. Wow, a lot of letters. So we're just going to say that fluorine has the highest electronegativity, and francium has the lowest. Now, the reason why we talk about electronegativity and why it's important is because it deals with compounds. The fact that it deals with compounds, that actually is going to tell us what kind of bond is in the compound, whether it's an ionic bond or a covalent bond. So that's a little bit later, but that's some foreshadowing. Okay, so again, francium has the smallest, and the trend goes like this. It increases going this way. Okay? So those are the periodic trends, and those are the patterns that we've developed on the periodic table because we know about the electron configuration and the way the electrons are. So have a great day, and talk to you later.